3.9, day number 2, derivatives of exponential and logarithmic functions. So let's get started by using the difference quotient to find the derivative of e to the x. We already know that the derivative of e to the x, based on our rule, is itself, but let's just confirm using the difference quotient. So let's take the limit as h goes to 0 of e to the x plus h minus e to the x all over h. If we do a little manipulation on this piece right here, we could write this as the limit as h goes to 0 of e to the x times e to the h minus e to the x. And you might see that there's a little bit more manipulation we can do here. One more step. This would be the limit as h goes to 0 of e to the x times e to the h minus 1 over h. Now this, you might hit a wall here and not be quite sure what to do, but if you use your graphing calculator, this piece right here, e to the h minus 1 over h, goes to 1 as h goes to 0. So we're left with e to the x after that limit is evaluated. Okay, so let's move on to finding the derivative of y equals a to the x. Let's go ahead and start by writing out, as it says here, y equals a to the x. And let's write that as y equals e to the ln of a to the x. We could then manipulate writing that again, bring that x down in front as y equals e to the x times ln of a. Okay, now we can take the derivative there. So if we take the derivative with respect to x, the derivative of e to the anything is that same thing. And then using the chain rule, we can take the derivative of the inside, which is the exponent here. And x times the natural log of a will be, derivative of that will just be the natural log of a. So then y prime will equal, again, this was a to the x, and this is the natural log of a. So in the next example, we've basically done that, right? So the derivative of 3 to the power of x would be 3 to the power of x times the natural log of 3. Right? And that'll follow suit on any base. So let's just curiously look back at this. Y equals e to the x. Well, that'd be using this rule, because it is an exponential, e to the x times the natural log of e. We said it was just, the derivative was this. Well, and it is, because this equals 1. Alright, let's do the natural log of x now. Let's use this method here and solve for x and then differentiate implicitly. So if I solve for x, I get that. If I differentiate implicitly, I do d dx. That would be e to the y times the derivative of y, which is the chain rule. That will equal 1. So dy dx equals 1 over e to the y. Well, what is e to the y? E to the y equals x. So dy dx, remember e to the y equals x. Therefore the derivative of the natural log, so d dx of the natural log of x equals 1 over x. Alright, so let's look at this example for y equals log base a of x. So we're going to rewrite in terms of, we're going to rewrite x in terms of y, so x would equal a to the y. Now let's take the derivative of this implicitly, d dx, derivative with respect to x of x is 1. A to the y would be a to the y. We form this formula on the last page, and then we can't forget we got to do chain rule and take the derivative of y with respect to x as well. So it looks like 1 over a to the y times natural log of a would equal the derivative of y with respect to x. And recall that a to the y equaled x, therefore the derivative of log base a of x will be 1 over x natural log of a. Okay, let's look at an example here on the next part. Example 5, find the derivative if y equals log base a of a to the sine x. So for a moment, let's treat it very similarly to the last problem. Okay, so the derivative of log base a of a to the x. So let's treat this as a logarithm first with a base of a and what we'd call, right, we're used to seeing, or we just saw in the previous problem, log base a of x. Okay, so the derivative of this, if we don't use the chain rule immediately, the derivative of this, our function, would be 1 over a to the sine x times natural log of a. Right? So just like we had up here, we had x times ln of a, we'll have x, which is a to the sine x, times ln of the base. Right? Now we have to use chain rule. This will be the derivative of the inside. This is now going to be the derivative with respect to x of a to the sine x. Right? Which again, if we use our properties of logs from earlier, the derivative with respect to x of a to the x was a to the x times natural log of a. Okay, so that's going to be a to the sine x times the natural log of a times chain rule on the inside, which is the derivative of sine x. It's cosine x. So notice something very crazy happens here. A to the sine x cancels, natural log of a cancels, and it looks like our derivative of this function is just cosine of x. Alright, so let's review these real quick, and then we'll get into some fun differentiation. Derivative of e to the x is itself. Derivative of a to the x is a to the x natural log of a. Derivative of natural log of x is 1 over x. Derivative of log base a of x is 1 over x times the natural log of a. And the derivative, we didn't cover this in this set of notes, but we did in the last one, of the absolute value of x is x over the absolute value of x. Alright, we're going to do some crazy differentiation here coming up. The steps you can see here, you can pause the video if you'd like. I'm just going to run through some of it. But we're going to use the natural log in order to solve some of these crazy derivatives. So I'm going to go ahead and do a little bit off camera with this first one, and then we'll do the rest together. Okay, so you can see I took the natural log of both sides of this function. And the reason I did that was so that I could pull this, this x up here out in front. And now when I do the derivative implicitly, the natural log of y would be 1 over y. Chain rule would say that I'd have to take then the derivative of the inside, which was y, so the derivative of y is dy dx. On the other side, I'm going to use product rule, so the derivative of the first is 1 times the second, plus the derivative of the second, which is 1 over x times the first. So as I do a little bit of cleaning up here, right, I've got 1 over y times dy dx. On the right side, I've got natural log of x plus 1. And so dy dx In this case, I would leave probably in this form, multiply both sides by y, and I get natural log of x plus 1. Okay, if you wanted to, you could go ahead and distribute. This would be an alternate form that you could use. This would be y natural log of x plus y. But the last thing you would want to do is you'd want to resubstitute in for y, of course. Y is not going to be left in that form because we want the derivative with respect to x. So I'll use this first form and say that x to the power of x equal times the natural log of x plus 1. That would be the derivative with respect to x. Okay, and the second one, what I would do is take the natural log of both sides. So that's the natural log of y. And taking the natural log of x to the sine x allows me to bring sine x down in front. And then I differentiate implicitly. So again, I get 1 over y dy dx. And that's equal to the, again, the product rule. So the derivative of sine x is cosine x plus sine x times the derivative of natural log of x is 1 over x. And then I just do a little simplifying. Now I'm multiplying both of these terms by y. Oops, I'm going to need a little more space than that. So I'm going to leave cosine x natural log x plus sine x over x in this form, and I'm going to multiply them both by y. Well, what was y? Y equaled x to the power of sine x. And there's your derivative. Alright folks, so that's it for today. That's a pretty good job getting started there on some fun implicit differentiation and using these properties of derivatives of exponential and logarithms to do so. Have a great day. See you next time.